Swayamprabha. Digital India. Educated India.
It is my pleasure to welcome you again to this course. Last two classes we have seen in detail about Gauss elimination procedure, special form of Gauss elimination procedure, what is known as a tridiagonal matrix algorithm. In this class we are going to see one more direct method, what is known as a LU decomposition. LU decomposition, so A coefficient matrix, say for example has no 0 value element, it is a full matrix. In LU decomposition, matrix A is decomposed into two matrices such as L and U, where L refers to lower triangular matrix and U refers to upper triangular matrix, and it is shown here A is equal to LU, and in the form of a matrix notation it is shown here A coefficient matrix A11 to ANN. It is now decomposed into L matrix and U matrix, and structure of L matrix is given. It has diagonal element value as 1 and it has elements on the lower side of the diagonal as shown here from L to 1 and all the way up to last row. Values on the upper part of this L matrix are 0. The lower part of the diagonal element of the U matrix are 0 and it has values from the diagonal and all the way up to the upper part. So, in this case U11, U22, UNN are values along the diagonal and other upper side it is filled with values. So, procedure of LU decomposition and solution is given in this flow chart. So, given coefficient matrix equation A x is equal to b, that is the initial system. Now, coefficient matrix A is decomposed as L and U, product of L and U. Now, we rewrite the given equation A is equal to b as L U x equal to b. Now, in this we substitute U x equal to d. So, we write now L U x equal to b as L d equal to b. Now, when we solve this equation we get d known, and that is by forward substitution. Now, initially we define U x equal to d and we rewrite here. Now, in this d is known because we got it from the previous set L d is equal to b. Now, x is a unknown variable column vector and U is upper triangular matrix. So, when we do the product, and that should be equal to d column matrix. Now, when you solve this we get finally x. So, in LU decomposition there are additional steps in terms of decomposing the given matrix A in the form of L and U, and it, as you can observe, it has steps overlapping with steps involved in Gauss elimination procedure, that is forward elimination and backward substitution. Now, the question is how to find or how to decompose given coefficient matrix A into L and U. In other words, how to find element values in coefficient matrix L and U. A mathematics is already given, there is a recursive procedure, and what is shown here is the final steps in that recursive procedure. So, calculation of elements in L and U matrix. So, Lij equal to Aij, that is the original value, that is a value in the original coefficient matrix, minus summation k 1 to j minus 1 L I k into U k j, where j is less than or equal to I and I going from 1 to n. Similarly, for upper diagonal matrix U I j, there is another recursive relationship, that is what is also displayed here. This recursive relation gets reduced for the first j is equal to 1, the rule gets reduced to L I 1 is equal to A I 1, and for I is equal to 1, the upper triangular matrix U I j gets reduced to U 1 j is equal to A 1 j by L 1 1. Now, this sets first row elements for the case of U and first column elements for the case of L. Now, we try to have a sample code listing for that operation that we just now explained to get element values in coefficient matrix L and U. So, do for I is equal to 1 to n, L I 1 equal to A I 1. So, this step finds first column elements in L matrix. Similarly, for U 1 comma j, where j runs from 1 to n, A 1 j divided by L 1 1, and this gives first row elements for U matrix. Then we find out other elements in L matrix and U matrix with the help of recursive relationship we displayed just now. The same relationship is written in the form of a programming listing here. So, for j is equal to 2 to n, for I j to n, k 1 to j minus 1, you accumulate the sum of L I k and U k j, n do, then you find elements of coefficient matrix L. Similarly, for U matrix, that is also listed here. What is shown here is not actual program, it is only skeleton of what can go in the code meant for writing to find out LU decomposition. Any language can be used, what is shown here is based on Fortran coding language. So, once L and U are determined, solution to the equation, the original equation is obtained as explained here. A x equal to b is the original set of linear equation, where x is unknown column vector and the form of transpose it is given here. B is again known value matrix on the right hand side, that is also given in the form of a transpose here. We have decomposed the original A matrix into LU. So, we rewrite A as LU into x equal to b. So, solution is obtained in two steps. First, we write U x equal to y, where y is equal to y 1 to y n transpose, then L y is equal to b. So, solution is obtained as y 1 is equal to b 1 and y I is equal to this recursive relationship, and where I is equal to 2 to n, and x n, this is now by backward substitution, is again by recursive relationship as shown here. Let us explain the LU decomposition procedure and finding the solution with the help of a example. So, it is given here, find x of the unknown vector x y z with the coefficient matrix as shown here 1 2 4 3 8 14 2 6 13, and B matrix as shown here as 3 13 4. The first step is to get the LU decomposition of the given coefficient matrix, and we rewrite L as given here. So, L matrix has diagonal elements as 1 and L 2 1, L 3 1, L 3 2 are the elements in L matrix, and upper part of the L matrix are 0. Similarly, for U matrix, lower part of the matrix are 0 and you have along diagonal values U 1 1, U 2 2, U 3 3 and then upper part. So, if you multiply L and U and equate it to given coefficient, then you are able to find values of L and U, and that is what we are going to show here. So, if we multiply For example, this is 3 by 3 matrix, this is again 3 by 3 matrix. So, it is possible to multiply. So, 1 into u 1 1, that becomes a first element of the product matrix L u. Similarly, for other coefficient elements, you can observe, for example, last row L31 multiplying u 1 1 and then L32 multiplying u 1 2 plus L32 multiplying u 2 2, and you get similarly expression for all the elements in that product matrix L and u. This is equated to the original coefficient matrix A, that is what is shown here, A 1 2 4 3 8 14 2 6 13, and that is what is displayed here. Now, all that we do, we set up a equation, 3 equations. So, we have to use this to find entries in L and u. It is easier in this example, however, it is good to understand. So, u 1 1 directly gets a value of 1, u 1 2 gets a value of 2, and u 1 3 gets a value of 4. Now, we write equation for other entries. So, L 2 1 u 1 1 is equal to 3. If you substitute u 1 1, you get value for L 2 1 as 3. Similarly, L 2 1 u 1 2 plus u 2 2 is equal to 8. If you substitute values for u 2 2, we get, if you substitute values for u 1 2, you get values for u 2 2 as 2. You can extend this for the third row, and following the algebraic, you finally get values for u 2 3 as 2. Again, continue that exercise to find coefficient values in the L matrix, and all the steps are shown here, and you get values of L 3 1, L 3 2, and then remaining u 3 3. So, if you substitute, finally, we get LU decomposition of the given matrix as shown here. So, given matrix A is shown here is equal to product of L matrix and U matrix. As defined before, in L matrix, diagonal elements are having value of 1, and the lower part of the diagonal element, that is they are having value as 3 2 1, and upper part is having 0 value. Similarly, U matrix, you have values along the diagonal, and upper part again there are some values, but the lower part has 0 value. Now, once you find L and U decomposition of the given matrix, now we have to find the column vector x y z. So, to solve a system modification by LU decomposition, we need to follow the procedure as given below. So, given A, find L and U, which we have already done, and now set y is equal to u x, so that it becomes L y equal to b. Now, if you solve this, because L is now triangular system and y is now becoming unknown, and b is again known from the original set. So, when you solve this equation L y is equal to b, then we get y. Then once you get y, we have already defined y is equal to u x. Now, if you solve by backward substitution, you get x, and that is what is our initial interest. Let us apply this step for the example problem that we have just now explained. So, L is already obtained as shown here, and u was also obtained as shown here. So, L y is equal to b for the vector y as defined as y 1 y 2 y 3. Now, L y is equal to b. So, b value is also given in the problem, L is shown here, and y is y 1 2 y 3. Now, you can solve this by what is known as a forward substitution. If you perform operation from the top, for example, it is directly known y 1 is equal to 3. Now, perform the operation for the second row, we get 3 y 1 plus y 2 is equal to 13, y 1 is already determined, substitute, you get value y 2 to be 4. Now, from the last row, we get 2 y 1 plus y 2 plus y 3 is equal to 4. In this, y 2 is known, y 1 is known, solve for y 3, you get value of minus 3. So, in the setup L y is equal to b, we have now got y. So, once we set up this equation, we solve by backward substitution. You can immediately observe the last row. So, 3 into z equal to minus 6. If you solve, you get value of z to be minus 2. Now, take the second row. So, 2y plus 2z equal to 4, again value of z is known, substitute and you get value of y to be 4. Now, take the first row top equation. So, x plus 2y plus 4z equal to 3, and if you solve after substituting value of y and z, you get x value to be 3. So, final solution is x y z equal to 3 4 minus 2. So, we have explained, given a coefficient matrix, how to decompose into L and U and how to follow from there to get solution. First step is forward substitution using L matrix, the second step is backward substitution using U matrix. So, if you look at advantages with respect to Gauss elimination, it is very popular, it is easy to program, there is no need to store zeros either for L matrix or U matrix. So, if you observe carefully, the given coefficient matrix A is split into L and U, an upper triangular part for L has 0 value, lower triangular part for U has 0 value, and though they are actually represented in actual program or while doing the program to get L and U matrix, you do not handle zeros at all. Similarly, L matrix has value 1 along the diagonal because it is fixed for any coefficient matrix and it will not be stored. Instead, one is possible to store coefficient values of U matrix in L matrix itself, wherever zeros are appearing in L matrix. Hence, finally, though it appears as if given matrix A is split into two different matrix, in actual coding it is not so. The given matrix A itself is used to store both L and U as shown here. So, given matrix A 1 1, A 1 2, A 1 n all the way up to A n n is now replaced with L and U as shown here. We already know for L matrix diagonal elements values are 1, and we also just now mentioned there is no need to store 1 because it is default for any coefficient matrix. That place is used to store values of U matrix U 1 1 along the diagonal all the way up to U n n, and upper part of L matrix has 0 value and that is used to store U matrix as shown here U 1 2 all the way other elements. Hence, the given coefficient matrix A itself is used to write L and U. So, this becomes easier to program and it also becomes very popular because it is easy to solve any matrix. So, in today's class particularly we talked in detail about LU decomposition way of solving a given coefficient matrix. We explained procedure with the help of a simple example problem. We also listed a sample coding structure. It is possible to write the code in any language appropriately for getting LU decomposition and then proceed to get answer for a given coefficient matrix. Next class we will talk about another procedure, what is known as the iterative procedure. Thank you.